not actually. Happens. Oh, that's a problem again. Somehow I cannot. Yeah. It is there, but not here. Yeah. A slide rather. Well, this weekend. I mean, no, it is better if we escape and escape. No, let's view. Slideshow. Okay, that's it. Okay, that's great. Thanks a lot. Thanks a lot. Hope it works. So I start like this. No presentation.
It's a pleasure for me to introduce you Professor Poves. He's a famous expert of film model and graphic physics. Let's enjoy.
Okay, thank you. Okay, good morning. It's Monday morning. We're 5 minutes late. So we're inside the academic rules. So I hope you enjoyed the first week of the school, and I'll try to keep on with the standards. Yeah, my idea is to convey to you a global idea of what is nuclear structure physics at low energy, incorporating many of the things that we have learned in the last years, which give us, in a sense, a perspective which is not written in the books. So essentially, we plan to conclude that what is written in the general books, it's not, I would say, not even wrong, as it's said sometimes. It's just marginal, I would say. Maybe because of the real complication of the difficulty of the things, but out of this difficulty associated to the fact that the atomic nucleus is a very complicated system. It's a many-body system with many particles interacting with a very complicated interaction. At the end of the day, I want to give you a bit of a new simplicity, which is completely at another level that the established simplicity, which essentially is very limited. Is no practical really interest or theoretical interest. Okay, so I will start, and maybe you all know that, but we have to fix the language and to be sure that what I'm telling you is meaningful. So most of the first hour or half an hour is extremely elementary and aim to fix the vocabulary, in a sense. So this is what I call undergraduate nuclear physics in a nutshell. And once we have fixed that, we can go on. The idea is to give an unified view of nuclear structure. Unified view means essentially that what you have learned as a dual manifestations of the nuclear dynamics, which is single particle language and collective language, will be unified in something. So my aim is to arrive to a description of collectivity. Collectivity is something which is proper to nuclear physics. All the nuclear matter colleagues are very happy saying, well, more is different. And emergency is the key word. And so on, they are so happy. But all these things happen in a really brutal manner in nuclear physics already, in nuclear structure at low energy. And we will see many examples of this, which are of dramatic, this is very dramatic nature. So one of the messages at the end of the day will be that contrary to what is written in the books, the key element in nuclear physics is collectivity, the emergent phenomena, not the single particle degrees of freedom. The single particle degrees of freedoms are there more as a background, as a basis, than as the real physical problem. This will be the aim of the course. And in this sense, is a different view from what is written in most of the books. Well, many of the things, most of them, of the things technically are written in the books, but the story is different. My narrative is different. Okay. So from this undergraduate nuclear physics, I will introduce the interacting cell model as a way to unify everything. Then I will discuss in a not very common way the effective interaction, because finally it will be the effective nuclear interaction that will produce all the physics. It's weird, Hamiltonian driven. So once you know your interaction well, all the manifestations of this interaction will be easier to control and to describe, okay? And with these tools, with this brick, I will go into collectivity. Once you have understood that the effective interaction, which are initially very complex, can be read in a simpler way, and once you can select which are the dominant correlators, the dominant part of the interactions that you have to deal with, then this interaction will be the protagonist of this emergency of collective coherent features of different nature. It could be superfluidity, it will be phonons, it could be permanent deformation of different types and associated rotational features. Okay? So this is the plan. So let's start from the very beginning. What are our starting hypotheses? First, we use nucleons. We don't use quarks or mesons, etc. We will use, it is not always necessary, non-relativistic kinematics. Sometimes you can use relativistic kinematics for working at low energies, but this is not a very fundamental issue. instead of solving a Schrödinger equation, you solve some kind of, at a given moment, you do some Dirac stuff, but it's not a basic issue if you want to describe collectivity, because even if you start with a non-relativistic kinematics, at the end of the day, you want to treat collective phenomena, you come back to things that are very similar to what you do in non-relativistic kinematics. Well, these neutrons and protons are bound by the strong nuclear interaction, which is just the projection of quantum chromodynamics in the space of neutrons and protons. And this, from the very start, is the origin of the complication. It is not that QCD is a very simple theory, because it's strong and low energy. It cannot be, the problem cannot be solved in perturbation theory. And so we are still at the stage where describing one single nucleon with QCD, it is a serious problem. You should use non-perturbative methods and do lattice QCD and whatnot. And even so, you cannot really pretend that you understand the proton ab initio, in a sense. So imagine if you go to lead 208. It is not probably the correct road to proceed. Not for the moment, at least. So as the interaction is a reduction of QCD to the space of the nucleons, you have the usual problems. When you reduce the, you can have a very simple interaction between elementary constituents, and if you need to change the protagonist of your problem because of having too many, for instance, the price to pay, and this is effective interaction theory, this will happen this will be coming all the time along. The price to pay to have simpler constituents is to complicate the interaction. Imagine atomic physics. We have only the Coulomb potential, which is simple and well known. And you solve your atomic problem. Okay, you can solve it. You can solve the simplest problems, and even the heavy atoms, you can solve the problem. Okay, but when you go to molecules, then you have many electrons in each atom, and even if the interaction is simple, to proceed and treat both all the nuclei which are there in the molecule and all the electron is not the way to proceed. What you do is to project into the space of the coordinates of the nuclei and forget about the electrons. And when you reduce this, when you eliminate all the electrons, etc., and reduce to the coordinates of the two of the atoms, in a sense, you get a new interaction, which is no longer the Coulomb interaction. Typically, in the case of noble gases, you get the van der Waals interaction. In the case of QCD and the nucleons, we're going to deal with a kind of van der Waals nuclear interactions. This is the reduction to the space of the nucleons, of all the complications of QCD. So we should expect complications. And in the case of the nuclear interaction, the complications are extremes in a sense. It is not only that the radial dependence of the interaction is different and more complicated, it is also the fact that all kind of terms, almost every term in the interaction that you can produce without violating the symmetry principles appears in the nuclear interaction that you have to build if you want to reproduce the phase shift and the properties of the nucleon, or of the two-nucleon system, which is the deuteron. And a little bit more with three-body, etc., that I will mention along. So this is a problem. The bare, let's call it bare nuclear interaction, has a very complicated form. Remember that you have a very strong, extremely strong short range of repulsion, followed by an intermediate range attraction, and then a tail which is simple in the sense that can be reproduced with just the fact that you exchange a pion. So our van der Waals interaction will have this kind of shape with an extremely short range repulsion, and this extremely short range repulsion is at the heart of many of the problems of nuclear theory. But this is just the radial part. But if you go to other terms of the interaction, you have, as you know, spin terms, spin orbit terms, and just to bother you even more, a novelty, which is probably a more complicated terms of interaction in physics, which is a tensor term. Tensor term is called like that because essentially it's an interaction in which you have kind of tensor of rank 2 in the normal space. The vector R is a vector, is a tensor of rank 1 in angular momentum. So it behaves as an angular momentum 1. So you can couple an angular momentum 1 and angular momentum 1 to make an angular momentum 2 and an operator of angular momentum 2. And this is a tensor of rank 2 under the rotational group O3. Okay? But you can do the same with the spins, because the spin, you can couple the two spins, which are again vectors in angular momentum, to a rank 2, and then you go back and you make a scalar, because all the Hamiltonian term, as the Hamiltonian is rotationally invariant, have to be scalars. Okay? But this is real complication, you know? This is a very, very extremely complicated thing. If you write this, remember that these are the Pauli matrices. You have to couple two Pauli matrices with Clebsch-Gordan coefficient. You have to couple the Cartan components of a vector. That you have to the vector in the Cartan basis, which is the angular momentum basis, and couple this object to a tensor of rank 2, and then recouple everything. So this is a mess. Okay? So the interaction, this is this point, has a complicated term. And the two complications, the two basic complications are this one, and sometimes this one. The other ones are less dramatic. Well, all these terms are needed to really describe the deuteron. Remember from your undergraduate courses that the need of the tensor force is forced by the fact that the deuteron has a quadruple moment which is different from 0, and the only way to have a quadruple moment different from 0 is to have a tensor term in your basic interaction. And you need everything to reproduce the phase shifts of the scattering of neutron-neutron, neutron-proton, and proton-proton, which is the basis of data, and you have many, many data, and you fit, really, you don't deduce at the present moment completely the interaction from first principle. You put the terms and fit the parameters. You can reduce in many ways the number, the phenomenology, if you want, of this nuclear-nuclear interaction. One way is just to use an effective theory, effective field theory, in which instead of quantum chromodynamics, you have pions and mesons. It's an effective theory of another rank, which has quanta which are effective also, like pions or sigmas or omegas or rhos. All these mesons give you shapes, and with that you reduce the number of parameters. Another way which is very popular, another route which is very popular nowadays, is chiral perturbation theory, which is a way of keeping the connection with quantum chromodynamics in the limit of chiral limits. In this theory, or approximation, if you want, you have a kind of perturbation derivation in which, at order by order, you get different terms. Some terms are fixed, or some relations are fixed by the rules of quantum chromodynamics, but there is less, but still a few or quite a few parameters that you have to fit to the experimental data. This is the state of the art today with the effective interaction at the two nucleon level. And this is only our ingredient, because our main aim has to do with the many-body aspect of the system. Many-body is not two, it is not three. Many-body would be probably more than 12. Less than 12, call it few-body for your files. Okay, with all these terms, we can describe the deuteron and the nuclear-nuclear scattering, and then I'm just reviewing the books. In the books of nuclear physics, you have the nuclear-nuclear interaction, and then they explain to you all these things, and you go to the deuteron, you're very happy, because you reproduce the quadrupole moment of the deuteron and whatnot, and the energy and the radius and whatnot. And then you change to the many body and you forget about that. Then this interaction disappears completely. Do you remember that this complicated interaction disappears in the book? In most of the books, go to the Crane or to the book of the Poves, etc. One of those, the books, the undergraduate books, and then this interaction disappears forever, more or less. More or less. That's what I was mentioning there. Typically for A greater than 12, the free space nuclear interaction is forgotten. And then you go straight to models. And the two models that appear are drop. Make a critique of that. But basic experimental facts that you study is which nuclei are stable, how much which is the mass of the nucleus, because the mass is the sum of the masses of the constituents less the interaction energy, and the interaction energy is just the again values of the Hamiltonian. Okay, so all the physics is contained in this mass effect. It's the global information is the difference between the sum of all the masses and the mass of the total nucleus. And we know that for medium and heavy mass nuclei, the binding energy, this interaction energy per particle is roughly constant. This is what is called nuclear saturation. And has to do with many things. This is a difficult problem in itself, but waving hands, you will say that the nuclear-nuclear interaction is short range and is some kind of saturates because the nucleons only interact with the closest, with the other nucleons that are close to them because of this short range. It's more complicated than that, but maybe we can live with it. And at the same time, another observable is the size of the nucleus. Which is the size of the nucleus? And the size of the nucleus grows in such a way that the density is roughly constant. So nucleus grows and grows, and the density is constant. So the radius grows like the number of nucleons to the power 1/3 to keep the density constant. Okay. This is at variance with many other systems. For instance, the atoms. There is no saturation in atomic physics. The atoms are roughly the same size, and the binding energy per particle grows as the power of the number of electrons. So because the Coulomb interaction is long range, while this interaction is different. Okay, but this saturation is what leads to the OLED in past time, to the model we call liquid drop, because in a liquid drop you have these properties. In a quantum liquid drops or classic liquid drop, you have that the density is constant independently of the size of the drop, because you don't change the density. The energy that goes to take an atom out of the drop is constant, so the binding energy per particle is constant. A liquid drop, molecular liquid drop, has these two properties of saturation. And you describe the liquid drop simply in terms of the number of particles you have, and then you characterize it via a volume term, which depends only on the total number of particles. And then, if you have a droplet, you have surface effect, because in the surface you have less interaction, and you have less neighbors, so you have the surface term, which goes like a to the 2/3. Well, but this is not a very good drop for our nucleus, because in the nucleus we have neutrons and protons, and the protons have the Coulomb repulsion. So you have to take into account your droplet is charged, so you have a Coulomb term which takes into account. But if you make with this formula, what you want to reproduce is the binding energy per particle, or the binding energy of the system, which experimentally, if you represent the binding energy per particle as a function of A, you get something which is typically like this. This band is small, so this can be considered in first approximation. If you had only the volume term, you will have a constant, but you have other terms, for instance, the surface, etc. You want to reproduce this experimental data with a formula, well, with these two terms plus a Coulomb term, you will more or less reproduce that. So if you add this term, which is the Coulomb repulsion, and these two terms, and your experimental data are here, well, you can manage to reproduce the data. But why this is a catastrophe? Why this, even if this reproduce the experimental data, well, why this is not a good description? Sorry? Well, this is too complicated. You're going too far. There is, huh? No, more simpler. Be simple. Because there is not only the masses, but only, I was being a bit tricky. You have to combine that with another thing that is, well, it is written there, so you can take advantage of the transparencies. At the same time, you have not only the binding energy per particle, you have another observable which is extremely important, which is which nuclei are stable as a function of the ratio between the neutrons and the protons. And then if you put n, you represent which are the stable nuclei in a plot where you put C and N. You start with more or less N equals C, and then you start moving. This is a band, in a sense. Huh? And you just, here more or less you have a stable nuclei, which is calcium 40, which, as you know, has N equal 20 and C equal 20. But at the end of the day, when you go up in mass, you go to lead 208, where you have 82 and 126. But what will be the prediction of a mass formula with these three terms? Which will be the line of stability predicted by this elementary formula? No more, just neutrons. Only neutrons. Because you gain energy just eliminating the Coulomb repulsion. Okay? So if you just have these three terms in your formula, the prediction of the line of stability will be this one, which is obviously wrong. So somehow, this is not the solution, because we have nuclei, not only neutron drops. Well, here we have a problem. This is not really. Is the fact that we have two fluids, two kind of particles in molecular drops. We were thinking in one drop of the same kind. So we need to do something. And one thing is, and we will do that explicitly, one thing is Pauli principle. The Pauli principle favors to have the same number of neutrons and protons. We will see that in an independent particle model. And another point is that it's dynamical. Means that on average, the nucleon-nucleon interaction, the nuclear interaction among neutrons and protons is more attractive than those between protons, nuclear interaction between proton-proton and neutron-neutron. So as in average, the neutron-proton interaction is more attractive, you prefer to minimize the energy to have the same number of protons and neutrons. Well, all these things are synthesized in the term of the mass formula, which is called the symmetry term of the mass formula, which has which is proportional to n minus c squared. So as you depart from n minus c, you lose energy. So there is a competition, which is this shape of the line of stability is due to the competition between the symmetry term of the energy and the Coulomb repulsion. And there is a trade-off which produces these things. Okay? Okay. But this is not the end of the thing. So you start with a very simple thing, and then ad hoc, you start adding, complicating your drop. Your drop was very simple at the beginning, but more and more you discover that it cannot encompass all the complexity, even of this single observable, or these basic properties associated to the mass, only to the mass. Next step is that on top of that, there is more information on which nuclei are stable and which nuclei. This is, gives you which is the ratio that correspond to the stability, but not fine details. And there is a funny detail, is that in this line you have almost 0 nuclei with an odd number of neutrons and an odd number of protons. And this in a drop, to play with odd or even for a drop, you will not pretend that the drop will know it. It has 120 molecules or 121 molecules. This is too much for these systems that essentially correspond to a limit of large number of constituents. Huh? So what to do with that? Well, now you were telling that. Now you add to your drop a paid-in term which favors the fact that you have an even number of protons and an even number of neutrons. And this is dynamics. So you're putting in something which is of a statistical nature or average nature, you are adding things that are not germane to the very theory. It's the paid-in term, which we will discuss in detail, and it is a dynamical term that is a manifest. We surprisingly, and this was really surprising for our predecessor, the energy you need to separate proton or to extract one proton, you represented it with respect to the number of neutrons and number of protons, had the same features that the ionization potential in atoms, in which you had this behavior in atoms. If you remember, when you represent the ionization potential, you have this famous behavior, yeah? with a kind of show behavior, and this maximum correspond to the noble gases. You have helium, argon, krypton, etc. And this is well understood and associated to the filling of atomic shells. And then you find more or less the same for a nucleus, which is like a drop, and you have shells in the drop. This is contradictory, absolutely contradictory. If there is one thing that is opposite, orthogonal to the idea of a drop, is to have shells which resemble an atomic system. So what? But this is put there, and you live with that for a while, no? But at the same time, if you have this, and this is what in my opinion, I haven't gone through the literature, But the surprise, in my opinion, was so big that people call the numbers that were in parallel to the atomic numbers corresponding to the noble gases, the number of magic numbers. And this is one of the pillars of the undergraduate nuclear physics. We start with the drop. We discover the magic nuclei, and then we go to make an atomic-like model for the nucleus, which is completely separated. But as you have to explain magic numbers, you need to have an independent particle description. Well, if nature tells you that, but you have two completely opposite views of the phenomenology of the system. So, in order to explain the magic number, we go to naive shell model or an independent particle model, and this makes a dichotomy. Liquid drop for fission and collectivity and whatever, and independent particle model for the magic numbers and so on. And this dichotomy is still in the books. And you have one chapter on the independent particle model. You remember the shell model, the quantum numbers, with one particle outside, etc. And then you go and compute happily the magnetic moment, and you're very happy because of the Smith lines, and very good. We continue with that. Then we try to compute quadrupole moment, and everything fails, and then we change chapter, and we start playing again with drops. That's what's in the books. No, I'm not. I'm just making a basic description of your previous knowledge. So, nuclei with proton and neutron numbers equal or very close to the magic numbers are treated as independent particles, global properties, and collective phenomena. You go back to your drop, and you quantize your drop, you deform your drop, you do whatever with your drop, and we continue happily living with these two models in a happy state of nuclear schizophrenia. And, well, my aim is to cure this mental state of the art, I would say, trying to unify the independent particle and collective excitation in a view which is based on, but going well beyond, the independent particle model. So, where am I? Let's continue being very simple and make an inventory of nuclear observables. Nuclei are quantum objects. We have, at low energy, discrete energy levels, and as the nuclear interaction is invariant under rotation, we will characterize this eigenstate of the Hamiltonian with the total angular momentum. We will use also the isospin, which is not a fully conserved quantum number, because there is symmetry, there is charge symmetry breaking terms in the interaction, not only the Coulomb term, but also basic other terms that are related, for instance, to the difference in mass in the neutrons and protons, and the fact that you have the quark content of the neutron and the proton is not the same, etc., etc. But all these corrections are tiny, and you can live with the isospin symmetry as a good dynamical symmetry, which is violated no more in general cases is good to 99%. Only in very exotic cases of definition you can have isospin, serious isospin. You can always have serious mixing with small interactions. And this happens when things are degenerated. And the idea that degeneration produces things will be another of the themes of these lectures. But this is another thing. Well, each state has a well-defined. Well-defined means that the width, every excited state, every state that decays, if you remember, is not an eigenstate of the full Hamiltonian. Maybe an eigenstate of the matter part of the Hamiltonian, but if it can decay, sending a photon out means that has a width, which is the inverse of the lifetime of the. But these widths are very small, so we can consider, in general, are very small, and we can consider that the energy is well defined. Not even the only energy that is completely well defined is that of the ground state of an unstable nuclei, and the only reason is that it has no other place where to go. And then the width is zero because the lifetime is infinite. But every state that has a lifetime different from zero has a certain width, a certain indefinition of the energy. And in a sense, every state in nuclear physics may be as a different entity. And we will see that as a characteristic, a very interesting characteristic of the system. So we can, in a sense, the fact that you know the ground state is not enough. The ground state may not contain all the information. So all the observables associated to the ground state, like the mass, the size, the magnetic moment, the quadrupole moment, all the observables that you want to know may be different in some excited states. So in the same nucleus, we can have different families of states. So we need to know these observables for each state. We need to know, if possible, and measure this state to know really what is the physics that is going on. These are the static properties, as I say, the magnetic moment, the size, the radius, the energy, etc., correspond to a single state. But then you can have all the decay properties that relate, where you have an initial state and a final state. Typically, as you know, in an even nucleus, you have typically a ground state which has parity. Well, I forgot about the parity. Parity is also a good quantum number because the electromagnetic and strong interaction commute with parity. And even if the weak interaction doesn't commute with parity, this is irrelevant. It doesn't mix it at all. So parity is a very good quantum number. Again, except if you have an extreme case of degeneracy where you can have a violation of parity. And we have cases. But it is only when really you have a state that so degenerate that can be extremely tiny but detectable parity mixing. Okay, so you have your excited state 2+, and he will not be there if you excite your nucleus to the 2+. It will not remain there all the time. After a certain time, it will emit a photon, a gamma ray, with the energy of the difference and with the angular momentum that you need, etc., etc. This is an E2 transition. From the lifetime, you can extract the probability that this transition take place. This is just the coupling is because of the coupling of the charge and current of the nucleus to the electromagnetic field, as you know very well. So you have all these decay properties coupling to the electromagnetic field with photons of different multipolarities. In some cases, you can decay to many states, etc. These are extremely interesting observables that will, in a sense, give you the fingerprint of which is the structure of the system you are dealing with. And you can also, and it is very important because it's at the basis of what is the nuclear stability, you can couple to the weak field. Coupling to a weak field in nuclear physics is to do beta decays, and we are in the place of the weak interaction. So this is a holy space, so to speak, to weak interaction. Was more or less invented here. So we couple to the weak field, and if you have a nucleus and changing a proton in a nucleus, you gain energy, relative energy. Then you can go to this other configuration, changing a nucleus and a proton, changing a neutron in a proton, just doing that, which is the beta decay of the neutron, with the emission of an electron and an antineutrino. But in the nuclear medium, a proton is stable, cannot go to the neutron because the neutron is heavier, so you cannot violate energy. But in the nuclear medium, what is relevant is the total balance of energy. So in the nuclear medium, a proton can decay to a neutron if this makes the full energy more favorable. So in the nuclear system, you have beta minus and beta plus decays. And again, you have lifetimes, you have branching ratios, all the observables associated to the coupling of the system to the weak field. Well, you can have many different ways. In the realm of the weak interaction, you have another very exotic decay mode, which is only possible in a few cases, which is the double beta decay. You can change at the same time 2 neutrons in 2 protons, because when the channel that goes to changing 1 neutron and 1 proton is not energy permitted, but you can have a channel which is permitted, which is changing 2 neutrons and 2 protons. And this is, if I have time, that meaning that if I change my pace, that I will not see. I had prepared something on neutrino, on the weak processes in nuclei, in particular because of the implication here in Italy of the search of the really exotic decay of 2 neutrino type, which is the neutrinoless double beta decay. The neutrinoless double beta decay has to do with the fact will exist if the neutrino is a Majorana particle. It means it's its own antiparticle. And the search for the neutrinoless double beta decay is one of the main points in nuclear particle mass nuclear physics, whatever you can want to call that, and takes place particularly here in Italy, in Gran Sasso, not very far from here, with 2 or 3 experiments going on, trying to find this very exotic process, and very important because it contains physics beyond the standard model of particle physics, and it will be will be a very, very important finding. This you have not only Gran Sasso, but there is a worldwide competition to go down in tunnels and mines to find this holy grail of the neutrino-less double beta decay. Okay, maybe if I have time. And other observable has to do with resonant excitation at high energy, but you can, where the idea of the widths are really larger than the idea of probably of discrete states is less clear. It's more of resonance, and there is all the world in resonance. And if I understand well, last week there was a course dealing with resonance and this kind of state by Volia. He was mentioning, at least in the title, there is something about resonant states. I don't know if... Okay. So, that's enough for the list of observables and a first review of where is this. And then we continue a bit still at the undergraduate level, and we fix a few concepts on. I don't know, how do you feel? Do you want to break for 5 minutes, or we can continue? I'm feel still alive. Huh? What do you want? Huh? Make it 5 minutes? Well, okay, let's go.